This lecture focuses on calorimetry, which, as you will see, is the measurement of the quantity of heat exchanged in a process. And you'll see that we'll call that quantity of heat lowercase q. So before we get going on calorimetry, let's remind you what we mean when we say endothermic and exothermic. Endothermic is a process by which the system, which is the substance that we're studying or the reaction that we're studying, absorbs heat from the surroundings. So when a system absorbs heat, it is called endothermic, and the mathematical value for heat is positive. On the other hand, when the system we're studying, typically a chemical reaction, releases heat to the surroundings, that process is called exothermic, and the mathematical sign for heat in that case is negative. Alrighty, calorimetry, what is that? Well, it's a fancy word for a process that measures the amount of heat transferred. And typically a calorimeter is an insulated device. So if you do it in the lab, it's typically with a styrofoam cup, sometimes a styrofoam cup that's nestled inside of a second styrofoam cup, and the inside cup has water in it, and then if you want to do some type of chemical reaction inside. And in the calorimeter there's a thermometer to measure temperature changes. Typically the reactions are conducted in water so that we can measure the temperature. You can't very well stick a thermometer in the middle of, usually in the middle of solid materials, and get a good temperature reading. It's also typically equipped with a stirrer so that the heat distribution is uniform. And most importantly, a calorimeter is insulated. Okay, so that means that any heat that is either released or absorbed stays within the system and its immediate surroundings rather than randomly released to the atmosphere. And so that we can assume that any heat that is either generated or absorbed is accurately recorded by the thermometer. Alright, so one of the most important things to understand when you're learning about the process of calorimetry is something called specific heat capacity. And I'm not sure why I'm writing it here because I see it right here. And you'll see when I give you the formula that we use when measuring by calorimetry, it has a term there called specific heat capacity, and that is abbreviated with a capital C. Specific heat capacity shows or demonstrates to us how sensitive a substance is to temperature changes. So as it turns out, every different material has its own unique specific heat capacity. Every material has a different degree of sensitivity to being heated. Okay? Some materials, when you heat them, will increase their temperature rapidly, and other materials will seem to be resistant to temperature increases. An example of that is water. Water has a very high specific heat capacity, so I'm just going to call it the capital C. Okay, so specific heat capacity of water is very high, which means it takes a lot of heat to get the temperature of water to change. So we're going to talk about specific heat capacity in a couple more slides because it's that important. So if you are one to take notes or jot something down as you listen to these pre-recorded lecture, specific heat capacity would be a really important one. So I'm just going to give you kind of different definitions of it. But another way to look at it is specific heat capacity is the measure of a substance's ability to absorb heat. So think of it as some substances don't really have the ability to take in heat and hold it. So instead, all of the heat they take in is used to increase temperature. Oh, there are my dogs. So the book definition of specific heat capacity It is the amount of heat energy that is needed to raise the temperature of that substance, and they're specific of 1 gram of that substance by 1 degree Celsius. So the units are joules over grams times Celsius. So let's think about the definition as we look at these units. Reread this definition. Specific heat capacity is the amount of heat energy. So joules is a measure of energy. So it's the amount of heat energy required to raise the temperature. So it's the amount of heat energy per degree Celsius, okay, and also per 1 gram of material. So that's where the units come from. That, my friend, will likely be a multiple choice question, the units of specific heat capacity. Alrighty, so looking at specific heat capacity of a variety of materials. As I said before, every substance has its own unique specific heat capacity or its own sensitivity to temperature changes. This is, I think, a good way to remember it. The higher the value of specific heat capacity, the more heat it takes to change temperature. So let's look at what has the highest heat capacity on this chart. It happens to be water. Water has a very high specific heat capacity. What did I say that means? A high specific heat capacity means that it takes more heat to change the temperature, okay? Which means essentially that water is resistant to temperature changes. If it takes more heat to change the temperature, that means it's resistant to temperature changes. Thank goodness that is, because water, I don't remember the percentage of water on our Earth. It's huge though, 70%, something like that, comparable to the amount of water in our body. And because most of our Earth is water, and because water resists temperature changes, we have a very moderate climate, a climate that's just perfect for life. All right, so to give you a visual example of what I mean by specific heat capacity, look at these 2 substances, gold and aluminum. They're both metals, but if you apply the same amount of heat to the same quantity, notice that we have a kilogram of each of them. Their densities are different, that's why they look different sizes, but the same mass and the same amount of heat, gold will increase by, call that the delta T, or change in temperature, 70 degrees Celsius, whereas aluminum change in temperature will only increase by, what is that? Should we say 30? Maybe about 10 degrees Celsius. Okay? In other words, gold changes its temperature about 7 times faster than does aluminum. Why is that? They've got the same amount of heat, the same quantity. It is because the specific heat of gold is very low. Gold is AU. Okay, specific heat of gold is very low. Remember, the lower the specific heat, the less heat is required to change the temperature. All right, let's talk again about the specific heat of water. I said that it had a very high specific heat, which means that it is very resistant to temperature changes. So let's talk specifically about what that means again. I talked about the large amounts of water on our Earth keeping our climate very moderate. So I'm sure you've been to the beach. If you go to the beach in the summer and you're barefoot, your feet feel like they're about ready to burn off because the land has increased in temperature a great deal during the day. Then you jump in the water and it suddenly feels quite cool. How is that possible? Because the water and the land have been exposed to the same amount of heat from the sun for the same amount of time. Well, that's primarily because the specific heat of water is very high and that of the ground or of sand is quite low. So also, I'm sure you see that water is very commonly used as a coolant, including in a radiator, old-time radiators in houses, and your automobile radiator. And that's because it can absorb a lot of heat and hang on to it, take the heat away from surrounding hot metals, and then not rise much itself in temperature, actually, literally. Okay, so now back to calorimetry. Calorimetry is a way to quantify or put numbers to the heat energy that's transferred in a process. So you remember what the calorimeter picture looked like. You have an insulated vessel, and inside that vessel you put whatever it is you want to study. If it's a chemical reaction, typically it's put in water, and a thermometer and stirrer put in, and the equation that you use to calculate heat is shown right here. Okay, so little q, think of that as quantity of heat. Little q stands for heat. Remember, the units for heat is joules. M stands for mass in grams. Capital C is the specific heat capacity. Delta T is the temperature change that is measured during the process. I like to call this the QMCAT equation. It's really not cat. I mean, delta T, that delta is not really an A, but it looks like an A to me. So I call that MCAT. It helps me remember the formula. Alrighty, so basically, the theory behind calorimetry and that using that formula are when any two substances are at different temperatures, heat will flow from the higher temperature material to the lower temperature material until both materials are at the same exact temperature. That's called thermal equilibrium. So I want you to remember when we're doing a calorimetry experiment, if you have two substances at different temperatures, that they are both going to have the same final temperature, because they will transfer heat from one to the other until they have both have the same final temperature. That's important in your calculations. Another way to look at that is the amount of heat that is lost by the cooler substance, by the hotter substance, is equal to the amount of heat that is gained by the cold material. So Q of the heat lost by the hot substance, is equal to Q, or heat, of the cooler substance. Obviously the math signs are going to be different. Okay, so we'll put a negative on one side and a positive on the other, but the absolute quantity will be the same. So let's get started trying to do an example anyway. Here's a very, very common calorimetry example. You have a block of metal that is hotter than room temperature. You may remember that room temperature is usually around 25 degrees Celsius. So you add this block of metal to water, and assuming you're adding it in a calorimeter in an insulated container, and you need to realize then that the thermal energy, or the heat, will transfer from the metal, because it's at a higher temperature, to the water, which is at a lower temperature, until both are at the same final temperature. I will call final temperature T sub F, okay, as opposed to initial temperature, which is T sub I. Now, delta temp T, which is the change in temperature between the two, would be TF minus TI. So kind of keep that in your back pocket. We'll need that. What do we need to do to calculate Q? Q equals MCAT, to help you remember the equation. What do we need? We need the mass of the material, we need the specific heat capacity of the material, and we need the change in temperature measured. Alright, so that was kind of a generic example to get you thinking about the quantities that you need. Here's a very specific example that I'm going to work with you. After I work this one, I would like you to try to work one on your own. If you're confident at all, go ahead and try this one on your own. My guess is you're probably going to need to watch me go through it, though. So here we go. A 32.5 gram cube of aluminum metal was submerged in water. The initial temperature of the metal, so I remember said to specify that, T sub I, for the metal is 45.8 degrees. we have the mass of the metal, we have the mass of water, we have the initial temperature of the metal, okay, that's of the metal, and we have the initial temperature of the water. Well, it was a little bit cooler than room temperature. So initial temperature of the water. Okay, what is the final temperature of both substances at thermal equilibrium? Realize that TF for both of these substances, like any two substances at different temperatures, will be the same, okay, because they're going to transfer heat until the TF is the same. All right, so let's look at the specific heat capacities we need. We need the specific heat capacity for everything involved. So we have aluminum. There's its specific heat capacity. And we put it in water. So here's the specific heat capacity of water. Look at the equation at the top of the page before I turn the page. Remember that the heat given away by the hotter metal is going to be equal to the heat absorbed by the water. The only difference is going to be a sign. We're going to put a negative sign in front of the material that is absorbing the heat. And so what we have the QMCAT equation for both substances. The substance that is giving away heat and the substance that is accepting the heat. Let's go to the next page and see what we have. All right, this is going to look real busy, so I'm going to take it very slowly. Again, the heat transferred from the aluminum block is equal, except for the minus sign, to the heat absorbed by the water. So we have to use the QMCAT equation for both the metal and the water. So the mass of aluminum is 32.5 grams. The specific heat of aluminum is 0.903. And we don't quite know the temperature change of aluminum, so we're going to leave that delta T. The mass of the water, don't forget you have to put a negative sign on one of these sides. Mass of the water is 105.3 grams. The specific heat capacity of water is 4.18. And again, we don't know changes in temperature, so we're going to leave that delta T. If you simplify this, just using a little bit of addition, subtraction, now it's more dividing, and combine the like terms, you are going to get something that looks like this. Okay, so this is a really important point. I want you to listen carefully at this point. Whenever you are solving for delta T, okay, if you're, well, not really delta T, but if you're trying to find the final temperature in a calorimetry experiment and all you've got is delta T, you need to write out what delta T is equal to. Delta T equals final temperature minus initial temperature. So anytime there's a delta T, you want to substitute in TF minus TI. And that's what we've done right here. Delta T of water is final temperature water minus initial temperature water. Same thing, delta T, change in temperature for aluminum, TF minus TI. So this is just a substitution, okay? Now, keep in mind that the initial temperatures are different. They started at different initial temperatures, but we know what those initial temperatures are, so we can plug in. And also keep in mind that TF, the final temperature, are going to be equal to each other, so we can combine the TF terms. So you're going to do a little bit of math. I want you to go through and make sure you understand how to do that. And you're going to rearrange the solve for TF, and it equals, I'm going to have to move this up. There we go. 17.3 degrees. That is the final temperature that both the aluminum block and the water are going to end up. Now, to just check so that you don't lose your common sense, whenever you do a QMCAT problem, the final temperature should be someplace in between the initial two temperatures. Here's TI for the aluminum, and there's Ti for the water. Okay, so your final temperature, which is 17.3, should be in between these two initial temperatures, and it is. Okay, it's much closer to the initial temperature of water. But it is in between those two. Alright, here is the second example. As soon as you finish this pre-recorded lecture, I recommend, if you haven't already, that you go to Mastering Chemistry, where the calorimetry problems are. Can't remember the section. It might be 6.6. I'm not sure. And start working some of those problems. So calorimetry is the first very important type of calculation you need to do from Chapter 6. So do a bunch of them. Alright, so here, and it's all going to be wording. And in some cases, you're going to be solving for Q heat. In other cases, you'll be solving for mass. And sometimes you'll be solving for specific heat capacity. And like we just did, sometimes you'll be solving for temperature. So I recommend, if you have any vague comfort at all with this equation, it really isn't a hard equation, I would recommend trying to do this problem on your own. To turn my lecture off, try to work it out on your own, struggle around, and come back and see if you do it right. If you're still totally lost, go ahead and listen to me one more time. Alright, so read the question. It's again asking you for initial temperature. So we have to get to WT, or excuse me, I don't know where that came from. We have to get to delta T, change in temperature. And so basically we're going to set it up like we did the last one, whereas the heat released by the aluminum is equal to minus the heat absorbed by the water. Okay? So another way to put that is the mass of the aluminum times specific heat capacity of the aluminum times change in temperature of the aluminum, oh, the doggies are back, equals minus the mass of the water. I hope you can listen to growling for a while. Specific heat capacity, that's just play growling, by the way, of water, and then change in temperature of the water. Okay, so it's really just a plug and chug, and then you got to be pretty good with rearranging in algebra. Alright, here we go. This is kind of what I just went over on the last page. Plugging everything in. The mass of water is 50 grams. Specific heat capacity is 4.18. Now, delta T of water is what you're trying to solve for. So, as I said, anytime you're trying to solve for something with delta T, remember that it is final temperature minus initial temperature. Go ahead and make your substitution anytime you see delta T. Now, in this case, we were given the final temperature instead of the initial. Oh my goodness. Okay. Here's the final temperature of water. Actually, final temperature is the same for both of them. All right. And we were given the original temperature of the aluminum block, 98 degrees. Okay. Ow! My foot got in the way. Sorry. Okay. So, let's plug in all the other data we know. 20 grams of water. Nope. 20 grams of aluminum. The specific heat capacity of aluminum, and final temperature of aluminum, and initial temperature of aluminum. And so now it's a matter of rearranging to solve for what you don't know. So practice that if you have, and this is algebra, if you have any trouble, come see me. If you want me to work it out for you, let me know, and I can probably do another quick one of these to show you how to do that. But give it a try yourself. Make sure that you come up with an initial temperature for water of 20 degrees Celsius. That is it for this pre-recorded lecture.